application of molarity in looking at dilutions. So our goal for today is that we will be able to predict the new molarity of a solution that has experienced a change in volume. So as a refresher, molarity, that was a way to describe the concentration of a solution. Okay, so it tells us how tightly packed those particles are in a given space. Okay. And we know we can calculate molarity by doing moles of solute over liters of total solution. Okay. So before we get into predicting new molarities, after we have a change in volume, we're going to do a little warm up. So let's say we have 50 milliliters of a 2 molar solution. We want to find how many moles of solute are present in that solution. So we can see that big M. That big M is our unit for molarity. And again, we know our equation for molarity is moles per liter. So if we look at this, we know our molarity is going to be 2. We don't know how many moles of solute we have. That's what we're trying to find. And we need to divide that by our volume in liters. Here, we're given 50 milliliters. So before we can figure out how many moles we have, we need to convert our 50 milliliters into liters. So as a refresher, we'll need to know this, that there are 1,000 milliliters in every 1 liter. So if we want milliliters to cancel out, we'll need to put milliliters on the bottom of that conversion factor. And we'll find that in the solution, we have a total volume of 0.05 liters. Okay. So that's just going to be a key conversion factor that we're going to need to know for this unit. Okay, that for every 1 liter, we have 1,000 milliliters. So if we have 50 milliliters, we're going to have 0.05 liters. Okay. So then we can plug that in for our volume in that molarity equation. So to solve for our moles of solute, or how many solute particles we have in the solution, we multiply each side by 0.05, and we'll find that we have 0.1 moles. So multiply both sides by 0.5 to get our moles of solute by itself, and we'll find that we have 0.1 moles of solute. Okay, and we found that just by using that molarity equation, moles of solute divided by our total volume. Okay, so now we're going to use that in number 2. So in number 2, we're asking if we increase the volume of the above solution by adding 50 milliliters of additional water, what is your new molarity? So let's picture this. In our original beaker, we had, let's say, 50 milliliters of solution, and we had 0.1 moles of solute dissolved in that water. Okay. In this problem, we add 50 more milliliters of water. So now, if we started out with originally 50 milliliters, after we add 50 milliliters more, our new volume is going to be 100. Okay, so we started with 50, we added 50 more, so now we have 100 milliliters total. In adding that water, our amount of particles didn't change. So we're still going to have our 0.1 moles of solute. Okay, so that's going to be a key idea here. Okay, so when we added water, or when we changed our volume, our number of particles per mole of solute stayed the same. The only difference now is that we have a larger volume. Those particles are just now more spread out. Okay? And if those particles are more spread out, that means our concentration went down. Okay, those particles are not as tightly packed. Okay? So when we want to find our new molarity here, okay, it's the moles of solute that are staying the same. How many particles we have did not change. The only thing that changed was how many milliliters of water we have that allowed those particles to spread out more. Okay. So in this one, if we want to find our new molarity, we're going to follow the same process. We're going to do moles divided by liters. Okay. So here, again, our number of moles did not change. We did not add or remove any of those solute particles. So take our 0.1 moles of solute and divide it by our volume. So if we did 50 milliliters plus 50 milliliters, our new volume then would be 100. And remember, we don't want that in milliliters, we want that in liters. And we know for every 1,000 milliliter, we have 1 liter. If we have 100 milliliters, that'd be equal to 0.1 liter. Okay. So the new volume of our solution is going to be 0.1. Okay, because now we have 100 milliliters of water rather than just 50. So when we do this, we're going to see that our new molarity is just going to be 1. It's 1 molar. Okay. And if we look at this, that 1 molar, that is going to be half as much as our original 2 molars. So compared to that original molarity of 2 molar, we're now at half that value. And that makes sense because the volume is now twice as large. Okay, so those particles were able to spread out twice as much, so our concentration is going to be half. Okay, and this is going to be the backbone of what we are looking at today. Okay, is when we add or remove water, our number of moles stayed the same. It's just that that change in volume is going to cause those particles to either become more far apart or closer together and cause our change in molarity. All right. What we saw in this example is going to be what we call a dilution. Okay. When we have a dilution, what we are doing is we are adding additional water. So when additional water is added to our aqueous solution. Okay, so our moles of particles stay the same. It's just that we're adding additional water. And when we're adding additional water, we saw that our particles could spread out more. And since our particles are spreading out more, that is causing us to have a decrease in molarity. So if you guys think of Kool-Aid, when you add more water to Kool-Aid, that Kool-Aid powder or those flavor crystals spread out more, so it doesn't taste as strong because you're not getting as many flavor crystals per sip. They're spreading out more. So when we're adding additional water, our particles are spreading out more. We're having a decrease in concentration. Okay. The opposite of dilution is going to be when we have evaporation. Okay, so this is similar to dilution in that our number of moles stay the same, but when water evaporates from our solution, that is going to cause our volume decrease. Okay, so this means our particles are going to have less room to move. Our particles are going to come closer together. And if those particles of solute come closer together, that's going to cause an increase in our concentration. So for each specific area, we're going to have more particles packed together. Okay, so let's go ahead and look at an example of where we have evaporation. We had a 300 milliliter solution of 1 molar Kool-Aid. Okay. We had our solution. Okay, it's at 300 milliliters. And we have however many particles. Okay. There's 300 milliliters of that 1 molar solution. Overnight, 25 milliliters evaporate. So that means if we started with 300 milliliters, 25 milliliters of water left and that it evaporated. So now we're only going to have 275 milliliters. When we have that evaporation, that's only going to contain water. So none of our Kool-Aid particles themselves are going to evaporate. It's just going to be the water. If we don't have Kool-Aid particles floating around in the air, while that would be very tasty, it just doesn't happen. So when we have this evaporation, the new volume of our solution is only going to be 275 milliliters, okay, because 25 milliliters left. So that means the 6 particles of Kool-Aid that we had are now going to be more compact. Okay, so that means our concentration is going to go up. And we want to find what that new molarity is going to be. Okay, so again, since our amount of water decreased, those Kool-Aid particles are more compact now, so our concentration is going to increase. So the way to do this is going to be the fact that we have the same number of moles of solute before and after the evaporation. Okay, so we have the same number moles of solute. Okay, so that solute didn't leave when water evaporated. So just like in that previous problem, the moles are going to be our bridge. Okay, we go away from our original solution to our new solution. So in deciding where to start, we want to look at which solution we have more information about. If we look at our original solution, we know our volume and our molarity, whereas our second solution, we only know the volume. So since we know more about that first solution, that's where we're going to start. Okay, because we know molarity is equal to moles per liter. Okay, and if I know my molarity is 1, and I know my volume is 300 milliliters, or 0.3 liters, okay, and again, I just got that 0.3 by dividing the 300 by 1,000. Okay, I'm able to find how many moles of Kool-Aid I have in my solution. Okay, so I multiply each side by 0.3. I'll find that my original solution had 0.3 moles of Kool-Aid. So since my number of particles didn't change and my number of moles of solute stayed the same, if I started with 0.3 moles of Kool-Aid, that means after the evaporation, I still needed to have 0.3 moles of Kool-Aid. Okay, so the number of moles of our solute stays the same. So then if we look at our new solution after the evaporation happened, now I know my moles and we know our volume, so we're able to solve for that new molarity. So we know we had 0.3 moles of Kool-Aid powder, and we have a total volume of 0.275 liters, which is our 275 milliliters. And when we do moles of solute divided by liters of solution, we'll find that our new molarity is going to be 1.09. Okay. So even though it was a slight amount, we do notice that our molarity increased because those particles are more closely compacted together. Okay. So the key for these dilution and evaporation problems is that your number of moles stay the same. So look to see, do you know more about your original solution or more about your new solution? Find those number of moles and use those to solve for your missing piece. Okay. So the key again, that we have the same number of moles before and after evaporation or the same number of moles before and after dilution. Okay. This is going to be the type of example you'll actually use in a chemistry lab. This is something I do all the time when we're doing labs and we need to make solutions in order to use for those labs. Okay. So let's say in the back storeroom, we have a 12 molar stock solution of HCl. Okay. So we have a solution with a molarity of 12. We want to make 500 milliliters of a 3 molar solution. Okay, so we have 12 molar. We want 500 milliliters of a 3 molar solution. So we want to dilute this. We want the solution to be not as strong or not as concentrated. So again, the key to be able to do this is when we have a dilution, okay, because we're making it not as concentrated, we're making the solution weaker, our number of moles stay the same. Okay, we can only change how much water we have. We cannot change how many moles of HCl we have. Okay? So we're going to look to see which side do we know more information of so that we can find our number of moles. Okay, because remember, the moles are the bridge to help us go from one solution to another. So if we look, we know more about the solution we want to make. We know we want 500 milliliters of a 3 molar solution. So remember, our equation for molarity is equal to moles per liter. So we know the molarity we want is 3. Okay, we don't know how many moles we'll need just yet, but we do know what volume of solution. Remember, always convert milliliters to liters. And when we do this, we'll find in order to make this solution, we'll need 1.5 moles of HCl. Okay. So in order to have 500 milliliters of a 3 molar solution, we need 1.5 moles of HCl. We are going to get this HCl, or this 1.5 moles, from our 12 molar stock solution. Okay. We just need to find what volume of that stock solution contains 1.5 moles. Okay. Because to make our desired solution, we need 1.5 moles of HCl. We're going to get that from the 12 molar stock solution. So we need to find what volume of that 12 molar stock solution contains the 1.5 moles of HCl. Okay. So now, if we look at our molarity equation again, we'll look to see that we know the molarity of the solution we're starting with. We know how many moles of HCl we need. We just need to find our volume. So again, what volume of that 12 molar solution contains 1.5 moles? Okay. Good first step here, whenever anything is in the denominator, multiply each side by that denominator. Get it out of the bottom. Okay. Because then we'll have 12B is equal to 1.5 moles. And we can see we're going to need to divide each side by 12. Okay. And when we do that, we'll find that we need a volume of 0.125 milliliters of our stock solution, or of that 12 molar solution. Okay. So in my beaker, I would want to add 0.125 liters of my 12 molar solution. Okay. Because that is the amount of solution that has the 1.5 moles that we need. However, if we look at this problem, we want a total volume of 500 milliliters. So right now in my beaker, I've only added 0.125 liters. I want to reach a total volume of 0.5. So at the moment, I am missing point 0.375 liters. Okay. So where this volume is going to come in that we're missing, that is going to be the water that we're going to add. Because remember, it's a dilution. And when we have a dilution, we're going to make it less concentrated by adding water. Okay. So when we took our 0.125 liters of 12 molar solution, that was still 12 molar. And we need to add water to dilute it or weaken it to our desired concentration. Okay. And since we wanted a total volume of 500 milliliters, if we only added 125 milliliters of that 12 molar solution, that told us we needed 375 milliliters of water. Okay. So in order to make this solution, we would need 0.125 liters or 125 milliliters of the 12 molar stock solution and 0.375 liters or 375 milliliters of water in order to make 500 milliliters of a 3 molar solution. Okay. So we need both these parts in our answer when we're describing how we can make a solution. We need what volume of the stock solution we need and what volume of water we're going to need to add to dilute it to the desired concentration. Okay, so to recap that one, because I know that was kind of a lot. When we are diluting a solution, the number of moles stays the same. So we found here, if we wanted to make 500 milliliters of a 3 molar solution, we would need 1.5 moles of HCl. We're going to get that 1.5 moles of HCl from our 12 molar stock solution. If we know the molarity and the number of moles that we need, we're able to solve for the volume that will contain that number of moles. So we found that we needed 0.125 milliliters of our stock solution. Okay. When we added that to our beaker, it was still 12 molar and it wasn't our desired volume, okay, because we only had 125 milliliters when we wanted 500. So we needed to make up that difference by adding water. Okay, that water did two things. Not only did it help us get to our desired volume, but it also diluted that 12 molar stock solution. Okay, it gave more room for those particles to move around in, made it less concentrated. So to make this solution, we would need 125 milliliters of a 12 molar stock solution and 375 milliliters of water to dilute it. Okay. All right. So again, guys, your first step, find your number of moles because the number of moles are going to be the same. Okay. All right. Have a great day. Let me know if you guys have any other questions.